Yeah, because that's okay, isn't it? Because of the formula.
Yeah, so
Yeah, proportional. Yeah. Yeah, so we're all right to continue, are we?
yeah.
Right, so we'll have to make up for Tiago's so let's just get started. Ideal gas law, let's go. Where's Zach? Okay, and Harry is sick, I think.
Yeah.
Alright, you got that, ideal gas law? Yeah, okay. There's a bit to do. Okay. Have you done ideal gas? No, we probably haven't with Lorraine yet. Ideal gas law. No, okay. Does anybody know Boyles Law? Yeah?
About, was it related to heat? Or was it the other one? No?
Pressure and volume.
Ah.
Come on, Zach. I know Tiago catches. Do you know Boyles Law? Ideal gas law. Boyles Law. Boyles Law states, for an ideal gas, pressure is proportional to 1 over volume, provided that the mass and temperature is held constant. So as a formula, pressure is proportional to 1 over volume. So what happens if the volume increases? What happens to the pressure?
Decreases.
Very good, yeah. Another way to write this is simply that PV is constant. Simply put, Boyle noted that if the volume is halved, then the pressure is doubled, or vice versa. What might other relationships be? Let's find out. Boyle was an Irish physicist from the north, I think. Okay? Yeah? Is it okay if I continue, Zach, or do you need a minute? Yeah.
So this is proportional.
Mm-hmm.
You know, in high school, this was inverse. For some reason, they put this.
It is
Inverse? Well, it is inversely proportional because of the 1 over V, but you're saying the symbol had a different meaning?
It's proportional to 1 over V. It's
Yeah.
inversely proportional to V.
Yeah,
But maybe she's saying her school had a special symbol for inversely proportional.
because this means inversely proportional for our school.
No, I don't believe that. That's shocking. I can't believe that. I refuse to believe that. You're going to have to find me one of your school books, okay?
Okay.
Right, continue.
Yeah.
It will not surprise you to know that temperature and pressure are related, obviously. From our day-to-day experience, we know that if the temperature increases, then what would happen to the pressure? Think about it. You increase. You see something getting hotter, like a gas,
More energy.
the pressure should increase. The pressure will increase too until kaboom, something explodes. Now, below is a graph of pressure and temperature. So what you have on this graph, I can just draw it again here for you. Nope, one better colour than that. I command you, Give me black. There we go. Just needs to know who's boss. Right. This is pressure in pascals, and we'll use temperature in Celsius. Okay. So let's take some gas. I don't know. It doesn't matter. Helium, whatever. And you heat it to a certain temperature, and you measure its pressure. Okay. And then you let it cool down, and you have a different temperature and a different pressure, and a different temperature, different pressure, and you do a few of these, and you get all these line up on a straight line, don't they? Now this isn't really surprising because we said temperature and pressure are proportional. We think that pressure is proportional to temperature. As the temperature goes up, the pressure goes up, and vice versa. Okay, so maybe for example, this is something like whatever, helium, just random example. Let's take another gas. I don't know, whatever, oxygen, and you measure different temperatures, you get different pressures, and if you draw the line, whoops, maybe. Get this. Yeah, what you know is if you keep doing this for different gases, interestingly, they all meet at the same point here. So even though your data is here, you can project the line backwards and you discover that they all meet at this point here. Now, can they go past this point? No, because the pressure will keep it positive, and here the pressure is 0 pascals. Yeah. Kelvin noticed this when he did this experiment. Kelvin noticed that if he continued all his graphs back, they would all meet at this point, which was minus about 273 Celsius. So he figured this must be the coldest possible temperature, because we can't go past this point on the graph. Yeah. So he called this point absolute zero, the coldest possible temperature you can have. In fact, it doesn't matter. It's for every material. Yeah. I think this is an important graph that you should have in your notes, because it's the graph that provides evidence for absolute zero and its calculation. Kelvin also Irish, I think.
Also, the degree Kelvins start at minus 273 and build up.
Yeah. Did you get your maths results? I know the highest score in your class.
For maths?
No 100s. 97. This is tough because the highest in my class is 100.
And the lowest?
I won't say the lowest, that's cruel. That's cruel.
Was it me?
Oh, I don't know actually. No, I don't think you were the lowest. Maybe the second lowest. No, I seriously, I don't know. I'm just teasing you. I'm just teasing. I just only, not that I only care about, I'm always interested in if anyone can get 100. But no, 97 was the highest, which is kind of painful. So close. Yeah. Okay, you got this graph? Yeah? Now, the definition of absolute zero is the lowest possible temperature any material can be at. Simple definition. Mm-hmm.
So what's the temperature of a vacuum? No material.
Minus 273, it's 0.15 Celsius above absolute zero is the temperature of a vacuum. Now you need to be thinking, why isn't it? Yeah, have a think about it. Tell me if you come up with a reason why. I'll tell you in a few minutes if you can't think of something. Continue.
Yep.
So we shall use this new scale. Diego, you mentioned this. This new scale called Kelvin. So explain again how the Kelvin scale works.
It starts at minus 273 then.
Yeah. So what is minus 273?
For Kelvin is
Yeah,
zero.
it's 0 Kelvin. Yeah. It's basically you move everything 273 units. So the temperature in Kelvin is the temperature in Celsius plus 273.15. By using Kelvin, the temperature is always positive, isn't it? It can never be negative. Formally, now I'll give you the formal definition of the Kelvin in a moment. You'll use Kelvin in chemistry, I'm sure, too, right? If you've not already used it. Not yet? Use Celsius? Or no questions with temperature yet? No, okay. Okay, got that? Yeah? The Kelvin is a scale of temperature. So in physics, when you want to make a new temperature scale, you need to define 2 points on the scale. So we've only actually defined 1 point on the scale. We've said that 0 Kelvin is absolute zero, minus 273. But we're supposed to define 2 points on the scale. So the Kelvin is a scale of temperature with absolute zero as 0 Kelvin. Fine. Does anybody know what is the other point on the scale? We need to define 2 points. So we need to say the Kelvin has absolute zero as 0 Kelvin and blank as blank Kelvin. Does anyone know the other point on the Kelvin scale definition? Yeah, what do you think? No, go on. What are you going to say?
No, I got it wrong.
Go
Would it be
on.
where in Celsius
What are we gonna
it's
say?
0?
Could be. Yes, could be. So the other point is that the triple point of water is 273.16. That is, roughly speaking, Zach, 0 Celsius.
Yeah.
So basically we're saying that the Kelvin, at 0 Kelvin we have absolute zero, and at 273 Kelvin we have this point called the triple point of water, which we don't have to worry about, but roughly speaking it's where water freezes. It's not technically that, it's just roughly that. But triple point is not a definition on this course. I don't even know if you've heard of this concept, triple point. No. Roughly speaking, it's where water freezes. But not exactly that.
But it says as exactly.
The triple point is exactly 273. And I'm just saying roughly what triple point means. Triple point means roughly the freezing point of water. Although it's not really that. And I feel bad telling you it's that, because it's not really that. But,
Is it? It is.
416.
huh?
416.
Yes, not 0.15. I know, this is what I'm saying. I'm kind of sidestepping exactly what triple point means, because if it did mean the freezing point, it should be 273.15. So I'm kind of slightly sort of, freezing point roughly, because it's a bit more complicated than what we need. Okay, but if anybody's interested, you can YouTube an explanation of triple point. If you want a little, few 5-minute video of someone explaining that, you can look at that later if you're interested. Okay, before I go on, the question I gave to Zach, he asked me what is the temperature of a vacuum, and it's not 0 Kelvin, it's roughly about 0.15, maybe a little less, maybe a little more Kelvin. Does anyone know the reason why a vacuum is not 0 Kelvin? Good guess, but no. Let's make the vacuum completely dark, so not light. Let us have the vacuum in deep space, away from any stars.
You always have something like
Dark
remaining
matter.
energy
Remaining energy from what?
from the Big Bang.
Correct. That's it. That's it. So that's why it's not 0 Kelvin. It's not.
You are
So there's no.
taking a slightly bit of energy from.
Yes, you are correct. Yes. No, slightly. 0.1 Kelvin. So
What is the
very
energy manifested as?
it's kind of a background radiation. This was discovered about 50 years ago when they were looking at deep space with radio telescopes, and they were picking up static, and they thought the static was the machine was faulty, but actually the static was the radiation in the vacuum from the Big Bang. So it's interesting. It's interesting. Okay, continue. You got that, yeah? Oh, I should actually also say that 0 Kelvin doesn't occur in nature, because the smallest temperature is roughly 0.15, something like this, in deep space. But I think maybe 3 years ago in the UK, I can't remember which lab, but they managed to achieve practically 0 Kelvin. I think they got the temperature down to 0.01 Kelvin, which, think about, is quite amazing. That makes that spot the coldest spot in the universe, provided no other aliens are doing the same experiment. It's quite amazing. It's very, very difficult to get the temperature that low. Yeah. I can't remember which university it was. It's some university in the UK.
How big was the spot? What is the volume?
Oh, they did it with something like tiny, 10 atoms or something. So something microscopic, to make it easier. It's already quite difficult to do. No, it's not like a room you could walk into or something. Yeah. Right. Okay. Let's continue. This is something that you might know from chemistry. But how do we count in physics? Like, when we count, we need a scale. For example, if we had some water, we do not say we have 10 to the 23 molecules of water. We need a unit to count. For example, bakers count in 13s. You know this?
Baker's dozen.
Baker's dozen, yeah. So you'd have 1, 2, 3, that is 39 for a baker, because they count in 13s, So 10 baker's dozens would be 130, right? Of course, in physics, we don't count in 13s. 13s is too small. We need to count in a different scale. So maybe you might say, maybe we should count in millions. I have 1 million molecules. I have 2 million molecules. No, even million is too small for us. We'll use something called Avogadro's constant. So in physics, when we need to count big things, we count in multiples of Avogadro's constant. And this gives us the definition of a mole. So, who knows the definition of a mole? A mole of something which can be counted, doesn't matter what it is, molecules, cups of coffee, stars, etc., is defined as 1 Avogadro constant of that something. And how big is 1 Avogadro's constant? Who knows this? Point
Times 10.
2
Oh, 2.
times 10 to the 23, yeah. Okay. But you told me you haven't done Avogadro in chemistry yet. Now, I don't want you to be confused about this. I want to be very clear. You can use Avogadro's constant to count anything. And if you have 1 mole of something, that means you have nearly 10 to the 24 of that thing. But you can count anything in moles. You could have a mole of H2O, which isn't actually much, you know, it's a small amount. You could have moles of cups of coffee, which would be a tremendous amount of cups of coffee. You could have a mole of stars. I don't know how many stars there are. That might be too many, actually. It just means I have 6 times 10 to the 23 of that thing. It's nothing fancy. That's all it is. Okay. Right. So imagine I have 1 mole of cups of coffee. That's a lot of coffee. Agreed? Yeah. What would the mass be? Okay. Small calculation question. Tell me what the mass of a mole of coffee cups would be.
The actual cups or the coffee?
Just the coffee inside
Just
the
the
cup.
coffee.
Yeah. Yeah. You'll have to estimate and do an estimation. But tell me what type of number you would expect this to be. Yeah, about mass. So
250 grams.
about this. Yeah. Yeah.
Avogadro's constant
Of cups of coffee.
So 2.5
0.
times 10 to the power 20.
Grams, is it? Or no, 26. You're giving me kilograms, is it?
No,
Grams,
grams.
yeah.
2 kilograms.
That's a lot, right? It's a lot. That's called the molar mass. The mass, when you have 1 mole, is called the molar mass. Yes? What's wrong? Are you listening? Molar mass means the mass of a mole of that material. Okay? So obviously for cups of coffee, that's a huge number. The molar mass of a material is defined as the mass of 1 mole of it. It's common to state this in grams. Now, the molar mass of cups of coffee is large. What might be a small example? Molar mass of what? Hydrogen, maybe. Molar mass of hydrogen would be not too big. Does anybody know what the mass is if you have a mole's worth of hydrogen?
In what grams?
Yeah.
One hydrogen atom is relative to.
I'll tell you. 1. So if you have 1 mole of hydrogen, then you'll have 1 gram of hydrogen. Okay. Now you may have heard the other one though, carbon 12. If you have a mole of carbon 12, you have 12 grams of carbon. Yeah. And you start to notice a pattern here. So if you have a mole of hydrogen 2, what's that called? Deuterium, you have 2 grams. So we start to see, moles are actually convenient because it means if you know your periodic table, there's a very easy way to work out the molar mass. You just have to look at the mass number. So take something like uranium. Uranium has a mass number of 238. So if you have 1 mole of uranium, then you have 238 grams of uranium. Yeah, it's quite convenient to use. For example, the molar mass of H2O, does anybody know this?
2 plus 6.
16 grams, is it? Is what you're saying? 18 roughly, 18 grams. So if you have a mole of H2O, you have 18 grams, which is only, like a little bit of water. That's a mole of water. Some important notation. Normally we use the letter big N to represent the number of molecules, and small n is the number of moles. And this is easy to remember. And we have a formula to relate the two. The number of molecules equals the number of moles times Avogadro. A famous chemistry formula, which you will see many times when you start it. In fact, you probably have seen it already in chemistry in high school. Yeah. Have you seen this formula before? You've seen it before?
How many moles react with how many
That
reacts
type
to
of stuff,
produce
yeah,
how
yeah,
many
yeah.
moles of-
Oh, have you done product and reactant with Lorraine?
No, not
Oh,
yet.
okay.
Done that.
What was the last thing you did with her? What topic are you on?
Doing intramolecular bonding.
The bonds.
Intermolecular bonding, sorry, shapes.
Ah, yeah, okay. Is that the stoichiometry? What's it called?
Yeah.
This-
stoichiometry.
The shapes.
No, that's the reaction.
Is it?
Yeah.
Okay. Right.
Stoichiometry.
Hint to remember. Big N is bigger than small n. That's how I remember it. So the number of molecules is a big number, so use big N. The number of moles is a small number, so use small n. Right. Here is a little chemistry warm-up question. Consider 1 litre of water at room temperature. Note that the molar mass of H2O is about 18 grams, gives you a mole. First question I'll let you do on your calculator is how many moles of H2O? Now before you start that, you need to tell me how many grams are in a litre of water. 1,000. Okay, now give me the first answer. What do we get?
Is it a constant on here?
Oh no. What answer did you get? Oh guys, you're thinking too much. I'm looking at your brains and you're thinking too much. What is it?
If there's that many
So
per
it's
mole,
just times
that's
1,000.
1,000.
So what answer do you have?
18.
Say again, sorry?
18015.
Nope. What do you get, sorry?
It's divided 1,000.
So what do you get?
8. Is that right?
What did you get? Thank you. Correct. I have one student awake. So, guys, you're overthinking. You're overthinking. How many grams in a litre? 1,000. Agreed? How many grams make a mole? 18. 1,000 divided by 18 is 55. Now you're making that face of not understanding when you should understand. No. What's wrong? What's wrong? It's not complicated, is it? How many grams in a litre? 1,000. How many grams make a mole? 18. How many moles in a litre? Well, how many 18 grams are in a litre? 1,000 divided by 18. Right? Yeah. Oh, Regina, I'm sorry, your classmates are just, they're not with it today. Right, try the second one for me. How many molecules of H2O are in 1 litre? Now, you know how many moles are there? 55, roughly. And 1 mole is how many molecules? 1 Avogadro. So, how many molecules are there? What do we do?
Times 5 over viscous.
Correct. And what does that give us? Gina, you got it? Yeah? Nice. Okay. Okay, next question is, how many oxygen atoms are in 1 litre of water?
Same as the last one.
Very good. The same as the last answer Gina gave us. And then lastly, how many hydrogen atoms are in 1 litre? Twice that previous answer. Oh no, Dorian, no, you're making that face too, like you now don't understand. What's the problem? And you're making that face too. So look. If I said there were 100 molecules, what am I saying? There's 100 H2O, which means there's 100 HHO. Right? Which means I'm saying that there's 200 H plus 100 O's.
No, we just do that.
Don't just do that with the big numbers, yeah. Yeah. Yeah? No, I don't know. What are we thinking? Dorian, what are you thinking? Is it okay or not? Not okay? Will you be okay? Well, you can watch this again later, maybe after lunch or something. I don't know. Really, you're having a bit of a brain freeze with this right now. Okay, all right.
I've always had problems with avocados and stuff.
Yeah, but this isn't really Avogadro. This is just counting, you know. I'm sure this will become a lot easier once you start doing it in chemistry many times. Many times, yeah. How are we doing? Okay, we're okay. It does. Look at the lid. It tells you the number. Yeah.
But does it have a specific button? Oh, the symbol. Shift 7 constant.
Yeah. It's what number is it on the calculator? It looks like NA. You have found it?
24.
24? Yeah. Okay, good.
Shift 7.
And then 24.
6,02214.
Yeah. Handy, isn't it? Yeah. This is why I recommend this calculator. Okay, continue. Yeah, continue. Yeah. Let's return to Boyles Law. It won't surprise you to learn there are other relationships. So, first relationship we did, Boyles Law. P proportional to 1 over V. Okay. The second relationship we did, pressure proportional to time. Not time, sorry. Temperature. Yeah. Volume is proportional to the number of molecules. Obviously, if you have twice the number of molecules, then the volume is twice as big, providing that you keep the density and other things constant, right? Obvious, I think. Pressure is also proportional to number of molecules. Now, here is a good question for the exam from last week. So tell me why this formula is true from yesterday's lesson. We could have known this from yesterday's lesson. Yeah. It's something to do with the proof we had at the start. So look, guys, look up. Remember the proof we did with the molecules in the box, right? And they were bouncing around, okay? And we calculated the change in momentum. And the change in momentum gave us a force. And the force gives us a what on the wall? A pressure with the area, yeah. Okay? What do you think would happen to the force if we have twice as many molecules hitting the wall? Twice the force. Therefore, what will happen to the pressure? Twice as well. So therefore, pressure is obviously proportional to the number of molecules. Because if you double how many molecules hit the wall, then you double the pressure. Because you're doubling the force.
Wouldn't it actually be more than double?
I don't see how.
Because they're not only colliding with the wall, but colliding with themselves.
Ah, yeah, but we only measure the pressure on the wall. So we do not care about internal actions. Yeah. Is that okay? And then the next relationship is volume. Now, we didn't talk about this one. Volume and temperature are proportional. If you heat the gas, it expands. You know this one. Yeah. It seems like all these are coming from one formula. You know, if we write all of these down, let's put them together. Pressure is proportional to 1 over volume. Pressure is proportional to temperature. What's the other one? Volume is proportional to number of moles. Pressure is proportional to number of moles. Volume is proportional to temperature. Now, if I just go to the side for the moment. If I said to you, X is proportional to Y times Z, if you keep the... X equals Y times Z. If the Y is constant, then you can say X is proportional to Z. Right? If the X is constant, then you can say YZ is equal to 1, which then means Y is proportional to 1 over Z. Okay, and so forth. What our job now is we need to look at all these formulas and think, what is the one formula that they're all coming from? So if we look at the first guy, P is proportional to 1 over V. So that probably means, are PV on the same side or different sides? Okay, so let's put it here on the left. Right. Pressure is proportional to temperature. The opposite side, yeah. Volume is proportional to N. So there's an N here, isn't there? Pressure is proportional to N. Well, actually, we have that already. And volume is proportional to temperature. We have that already. But the only problem is we don't really know if it's an equal here, because we could have some constant and the formulas still work. Like if I put a 2 here, you know. So we can say, right, well, maybe there's some constant in the formula which we don't know. So we end up with the formula pressure times volume equals number of moles times a constant, unknown constant at the moment, multiplied by temperature. Well, maybe this might look a little bit familiar for those who've studied it before. Has anyone seen this formula? No, this is a new one for you. This formula is called the ideal gas law, and it has 2 forms. If we use moles, we write it like this, but if we use molecules, we give the constant a different name. We call it K. Now what I'll do is I'll let you write that down, and then we'll continue next time from this point.
Why do they give them different symbols?
That has a long explanation, which will come up next time. I'll leave it on a cliffhanger for today. You know, mid-season finale. I have a bit of a dilemma. There's a meeting that I could go to. I don't have to go to it. The only problem is there's free sandwiches at it. The meeting might be nearly 2 hours long.
But you can do the, oh sorry, I have to go to the toilet.
I know, I was thinking this too. I could make some excuse halfway through, but free lunch is free lunch, you know. But a 2 hour meeting is tough.
But maybe it's interesting.
They never are. They never are. Okay, did you get that? Yeah, alright. We got class tomorrow? Monday, okay. We'll leave it hanging until Monday, so. Oh, well then that means you don't have homework, so this gives you plenty of time to work on your essay. Yes?
Thanks for giving us today off.
Oh yeah, you have a half day as well, yeah. I expect wonderful essays, so for next week.